Okay, so for your whole assignment that'll be due on Friday, basically it's going to work like this. You're going to enter a bunch of points, and then you're going to construct a hull that encloses those points. Let's see, 0, 3. And then I don't know if you have to do the bounding circle thing, but I make a bounding circle that encloses all of the points. And then what I do is I enter numbers, and those numbers can be in one of three places. They can be outside the bounding circle, they can be inside the bounding circle but outside the hole, or they can be inside both. And so the main thing is just getting the hole, construct the hole, and then test to see if things are inside the hole. The bounding circle is pretty easy to do. You just the center of a it's actually really easy to construct a bounding circle. Let me maybe do it visually for you guys. So let's see, IS50B. Here we go. Okay. So page hole bounding circle. So let's say that you've got a bunch of points. Okay. So here, 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 here. Okay. So when we construct our hole, we start by doing this. We do that, and because we sort them left to right, you know. And then we were like, oh, that's a left-hand turn. Throw those two away. Add that one. Add this one. Oh, that's a left-hand turn. Throw those two away. Add that one. Oh, that's a left-hand turn. Throw those two away. Add that one. And you have to keep checking. Every time you throw it away and add one, you have to still see if there's a left-hand turn. And then at the end of it, you end up with the upper hole, and then you do the same thing on the lower hole. So it's going to be here to here, then here to here. Oh, that's a left-hand turn. Throw it away. Add this one. Here to here. Here to here. Oh, left-hand turn. Do that one. And then there. Throw it away. Do that one. And that's the hole that you end up with. So let's say that you want to do a circle, a bounding circle that encompasses the whole thing. Well, you figure out what the maximum and minimum x and y values are, right? And so you can construct a axis line bounding box around it if you like. And you can do that test if you like, or you can just average the min and max values together, and that'll give you a center point. And you simply see what the of the points on the hole, which one is the longest away. If that one is away like 10, then what you do is you take that and you sweep it around in a circle. That's a really terrible circle of size 10, and that is a bounding circle. So you have your radius in the middle, average x and y value basically, and then you just go through every point on the hole, see which one's furthest away, and then that's the radius. And so you drag that in a circle around it, and then that can make tests pretty easy, right? So you can use AABB, which is this option here. And AABB is really easy to construct. You do that by just doing the min y, the max y, the min z x rather, and the max x. Apologies for the handwriting. Let's erase that. So you do the min x and the max x. And then if somebody says, hey, is that point within the hole? You can just do an AABB test. Is this between min x and max x? Is its y between min y and max y? If so, yes, it's within the AABB. Then you can do the complex hole test. And the complex hole is... I'll draw it in rainbow colors, I guess. Like that. So that's the complex hole, and then you've got a AABB here, and then whatever the center point of that is, it actually doesn't matter what you pick as the center point, really, because it's just a simple bounding circle like that is just to make your test faster. So it actually doesn't really matter where you pick the center point, but just averaging the x's and y's together, I guess, is one way of doing it. And then what you do is you just say, okay, it's 4 away from here, and it's 6 away from here, and it's 10 away from here. Okay, the radius is 10. And so what you do is you then sweep that out in a circle of size 10 from the radius. And then if you want to see if you're going to do a convex hole point content test, if you test to see if that point is within the hole, you first test it against the bounding sphere, a bounding circle, and you're like, okay, that's 12 away, it wouldn't be 12 away, that'd be 8 away. Okay, it's inside the circle. Then you do the complex test. So you do the simple test first, then you do the complex test. And you do this, it's to the right, this, it's to the left, fail. Okay. So, pre-traversals, in order, post-order, in order, breadth first search, no, has nothing to do with any of that. It's nothing to do with any of that. The algorithm is you maintain a stack, which is a vector. And so you're given like point A, point B, point C, point D, point E, and you sort them left to right. And you do a line segment. And so a line segment is just 2 points. And so you start by adding A, B to the complex hole. You start at the left, go to the right, A, B. And then you add B, C. And then you check to see if you made a left-hand turn. You check that by doing cross product. And the directory that I've given you does cross product already. It normalizes the vectors for you, so you don't even have to normalize them. You just pass in this vector and that vector, and you can do that by saying B minus A. That will give you that link there, the displacement vector, and C minus B is that displacement vector there. So you just cross product this times this, and if it gives you a positive number, it's to the left. Throw it away. And so if you every time you add a line segment, you just that should be B, C. Every time you add a line segment to the hole, you just add it onto the stack like that. It's just a vector, like you're just doing vector pushback BC. And then you cross product these two things. And if you get a positive number, then it's a left-hand turn. And what you do is you pop them off and push on A to C instead. So you pop A, B, and B, C, and you add AC, and you rinse and repeat until you get to the very last one. Okay, and there's always going to be at least one line segment on there, because let's say they're all left-hand turns. Like let's say E was up here. Eventually, you would throw away everything except for the A to E. Okay, and then you repeat by going down to the right, and so we finish with that. And then, so you go left to right on one of them, then you go right, you repeat it right to left, and that gives you the bottom half of the hole over here. So the first thing you have to do is construct the hole, and then the second thing you have to do is test to see if things are inside of the hole. That's it. Okay. Your stream isn't working. Seeing isn't even in the chat channel. Okay, it's okay. We're recording. Yep. So I guess for the input tester on this, I can make it even easier. So you don't even need to do a bounding sphere or whatever. Just tell me true or false. Is after you construct the sphere, the user is going to be passing in points here and here and here and here. You just tell me, is this inside the hole or not? That's it. And so how do you see if something's within the hole? Okay. Well, you've got all these different line segments, right? Let me do clean it up a little bit. And these things are all held clockwise because they have to be clockwise. This. And so if you have a point here, what you do is you compute the displacement vector x minus a, right? X minus a is the displacement vector of how you get from a to x, right? And then you've got point, I don't know, we're going to call this d over here, I guess. So the first line segment is a to d. So you say d minus a and x minus a, you cross product them. So you take x minus a and cross product it with d minus a, and you see if it's to the right, to the left. Okay. If it's to the right, yes. If it's to the left, no. Okay. And then you do it again from here to here. So you would compare, on this one, you would compare E minus D cross-producted with X minus D. So that vector here, X to D to X and D to E, you compute them by just doing a vector subtraction. And there's a header file that I gave you that does some of the linear algebra. It does the cross product for you. It's got a vector2 class. So you make a vector of pairs. No, it's already given to you, I think. Let me check. Vector linear.h maybe. There you go. Okay. So it's got a vector2. It's got a distance function that returns how far one is away from another one. That's distance squared. Comparison, double right arrow. It's got a circle class, it's got a length class, normalize, dot product, cross product. So it does not have subtraction. So you might want to do a subtraction operator to subtract two things. So if you have two points, you subtract them. That creates a displacement vector between them, which tells you how far you have to go from D to get to X. That's the displacement vector. It's computed by doing X minus D. And so what you do is you take this vector D to E, which you compute by E minus D, and this vector from D to X, which you compute with X minus X. You cross product them, and then you see, is the result positive or negative? If it's positive, it's one way. If it's negative, it's the other way. So the right or to the left. And which one it is just depends on which one of the two you put first. So just test it. Okay. It'll tell you, like, plus numbers will be that way, minus numbers are that way, or it's the other way around, just depending on which one of the vectors you do first. Just be consistent, and then do the same for this one and for this one. You do the same for this one and for this one. So you go around the circle, and if all of them say they're to the right, congratulations, it's in the hole. If any of them say they're to the left, it's outside of the hole. Okay. So it's not too bad, I don't think. Let's see, word count by a line, main.cc, it's 93 lines of code for all that. And I'm generating a bounding circle and doing a bounding circle test as well. Positive means left, means you need to pop two vectors off left and skip the point. Yeah, well, there's two phases. The first phase is constructing the hole, and which is, this part that we went through. And then the second phase, you have to test to see if a point is inside of a hole. Okay, so in the first phase, you're going to be adding line segments over and over again to a stack. And if you ever make a left-hand turn, and again, you compute the left-hand turn, like, let's just take a simple example. Let's say that A is at 0, 0 to make it life simple. All right, so it's here at the origin, the axis origin. Draw a little Cartesian coordinate system here. So A is at the origin, B is at 5, 5, and C is up here at 7, 10. Okay. So when you construct the hole, you start off by sorting all of the points left to right. That's step one to construct a hole. Step one, sort. Sort horizontally, and then you're going to repeat the following steps. Add next line segment to stack. Check if left turn. If so, pop 2, push 1. So you're going to pop A, B, B, C, get taken off, A to C gets added. Okay. So how do you do the math on that? Okay. So, so you start off, you push A to B on the stack, and it can't be a left turn because it's the first thing on the stack, so that's fine. And then you push B to C on the stack. Check to see if it's a left turn. How do you do that? You take B minus A, that's the displacement vector, that's going to be 5, 5. And you're going to cross product it with C minus B. C minus B is 2, 5. So B minus A is 5, 5. You're going to cross product it with 2, 5 because it's 2 to the right, 5 up. And so the cross product is going to be 25 minus 10, which is 15. Since it's a positive number, that's a left turn. Not allowed. So we take A and B to C off the stack. These guys come off the stack. And we pop 2, push 1. So we pop off A, B, B, C, and we push on A to C. So that's what's on the stack. 0, 0 to 7, 10. And then if there's another one, like up here, so D would be at like 9, 20 or something, you would say, all right, 7, 10 to 9. You repeat the process until there's nobody left to push. Once you hit the end, you're done. So try pushing on 9, 20, 7, 10. Cross product is going to be 90 minus, that's not 710, that's going to be 210. That's a 2, not a 7, because it's 2 to the right, 10 up, right? So it's going to be 90 minus 40, so the number here is 50, so that's positive, so that's a left-hand turn. So you pop off AC and CD, and you add on A to D instead. Now let's put E down here somewhere. It's going to be at like, this is E, and we'll say it's at 20 and 8. Like that. Oops. Okay, so we're going to push D to E on the stack. And so we cross product E minus D and D minus A. So these two things are going to get cross producted. E minus D is 11. 20 minus 9 is 11. 8 minus 20 is negative 12. Okay. And then A to D is 920. Am I doing this the same way I was before? I might have reversed the order. Yeah. Okay. And then 920. Might have reversed the order, in which case we're going to get the negative result. Like I said, you just have to be consistent. So the cross product of this is, was it 220 minus 108 plus 108? Yeah, I did it backwards. So it should be the other way around. It should be, was it 108 minus 220, which is a negative number, and so it's a right turn. Okay. Just don't switch the order you're doing the things. or the pluses become minuses and the minuses become pluses. So the cross product is this times this minus this times this. It's a cross product. That's what it's called a cross product. This times this minus this times this. Yep. What happens to B and C? They're gone. They're not used. They're going to stay in there when we go backwards, right? And so when we go backwards, we're going to they're still going to be in there in the original set of points for the backwards approach, because we're going to start going backwards. We're going to start with D to E, or E to D, cool. And then we're going to discover that C to D is a left-hand turn coming backwards. So when you do that, that's a left turn. And so becomes E to C instead. We then do this, and we discover that's a left-hand turn. So these two things come off. We put on E to B instead. We add B to A, and it looks around left-hand turn, probably a little bit. So E to B would come off, I don't know, whatever. I'll just leave it on there. It doesn't matter. No, it is a left-hand turn, isn't it? Okay. Then E to A would be the last one. No. Yeah, I don't know. I'm not drawing exactly a straight line. That's pretty close. But yeah, so C and B aren't necessarily deleted. Like they're still there for when you go backwards. But after you're done, all the points that are inside of here that aren't part of the whole, you can just discard them. They're not needed anymore, because they're only needed to construct the whole. Then once you've made the whole, you end up with, in this case, a triangle, right? So you're going to end up with, in this case, a triangle that encompasses all of these points. It doesn't have to be a triangle. It just kind of worked out that way. And then you just do that's phase one. So phase one is constructing the whole. And then phase two is saying, is this point in, is this point in, is this point in, and you're just going to do a point contents test, where you're just going to say, is this within the whole or is it not within the whole? And that's your homework assignment. So it's going to be a lot of cross products. So I would add in a operator for this. In fact, I can just do it right now for you guys. Alright, so linear.h. So we've got a vector 2, which is just a 2-element vector. So we can just add a little operator plus, operator minus. Why not? Let's do it. Okay, so vec2, operator plus, taking in a const vec2 by reference called right-hand side. And I guess we'll do the same for operator minus. Okay, so we are going to return our x plus their x. We're doing addition, right? We're returning our x plus their x and our y plus their y. And then for subtraction, it's just the same, but with minuses instead of pluses. And there you go. So that will allow you to do d minus a and x minus a and stuff like that. The dot product and cross product functions that take vec2s, they will normalize the vectors for you, so you don't need to worry about that. So unable to make Unreal work on my laptop. Okay, so yep. Oh yeah, here's some nice C++. So a vector 2 can mean anything, right? Or a vector 3 could, like sometimes we use vector 3s to hold colors, like RGB, because it's 3 numbers. A vector 3 is just any 3, doubles in a row. But sometimes we want to be more clear about what we're doing with it. And so in this case, we have a using statement. And so using statement says we're going to be using point as vector 2. Normally using statements are used to shorten a long type name. If you have a really long type name, or if you're using a namespace, you don't want to use the namespace anymore, Typically, we use usings to become less verbose. In this case, we're becoming more verbose. There's more typing to type out point than there is for a line or for a vec2. But we're doing this so that we're clear, right? That these are 2 points. We have a starting point and an ending point. And that's because a point is a vector too. There's no difference. I don't want to make a separate point class when it's all the same thing, but you can simply call it a point instead. And so this is a point for the start, point for the end. You could probably add in a cross product member function here, but I think the cross product is down here. Oh, this is a 3-point cross product. Okay, so this doesn't use 2 line segments. It takes 3 points, and so if you want to compute e minus d crossed with x minus d, what you pass it is d, e, and x. So you notice how they always share a point like this. So you pass in e, d, and x to the function here. So P1 is D, it's the common one, and then these are the two other points. Yeah, okay. You could make a cross product version that just takes 2 line segments and cross products them as well, if you like. Normalizes a vector by taking the length of it and then dividing each component by the length. Okay, so both names will point to the same address. Yeah, it's because I think when I wrote that, I realized there's no reason passing d in twice. You know what I mean? So rather than having to compute the displacement vector, which is extra math, right? You can just pass in d, x, and e. You just pass in the 3 points, and then it does the cross product for you. So it saves you from doing a vector subtract, and it saves you from using d twice, right? So it's probably a little bit more efficient. That's why I did that. Conceptually, it's the same thing. You just pass in this point x, this point d, this point e, and it will return a positive or a negative number. And so if it's, depending on the order you do it, if it's positive, it's to the left. If it's negative, it's to the right, usually. If you do DE, then XD. But it just depends which order you pass it in. You're asking about using? Yeah, so using is just an alias. It is a way of having a different name for the same thing. So the type of start and end are both vector2. But here, I'm just referring to it as point. Yeah. And so the center of a circle is a vector2, but I want to be clear that it's a point, right? It's not just 2 numbers. I conceive of the center point of a circle as a point. It's a point in space. It's a Cartesian point. Not some other use of a vec2, because a vec2 and a vec3 and a vec4 are just very generic data structures that are used in a lot of different contexts and have different meanings. And so I don't know, when I look at a vec3, is this holding an RGB color? Is it holding a point in 3D space? Is it holding a velocity, right? Because the velocity can also be held as a vec3, right? Because you've got velocity in the x direction, velocity in the y direction, velocity in the z direction. So I don't know if I'm holding a position or if I'm holding a velocity if I see vec3. Now you might call it velocity or whatever, but by using I can sort of tell future me what start means. You know, what is start? It's the starting point. It's the ending point, right, of the line. It's a line segment. And you know, like I said last time, another way you can hold a line segment is with 1 point and a slope and a length. And so that's another way you can do it. And that makes some of the math easier, because when you when you do the line intersection test, you'll get a distance along the slope that you get the intersect. You can check to see if that distance is between the length and 0. If it's below 0, you missed on one side. If it's above length, you missed on the other side. So that's that might be a nice function to add to this too, for line intersection tests. Not that we need it for this assignment. For this assignment, you're just going to be doing a lot of cross products. You're going to have a vector. The stack that I was talking about is just going to be a vector of lines. Yeah. And then you'll, every time you push something onto the stack, you cross product it with the previous, yeah, I don't know. You know what, this one won't work for that one. This cross product won't work for that because they don't share the same starting point. Probably have to add a cross product for this one. So I'm making it a friend function, so it's not actually a member function. So you don't call cross product on a line. You just call cross product, passing in two lines to it. So it's actually a global function, not a member function. And it doesn't technically need to be a friend because it's a struct. I'm just going all public on this. No getter, setters, none of that stuff. So cross product, it'll take 2 lines, left hand side, cross line, ampersand, right hand side. So it's going to take 2 line segments, and we want to see if it doesn't like that, does it? Because we have one named that already. Is that true? Type specifier for all we need a return type. Double. Okay. So we are going to cross product the 2 line segments. And so we are going to do this equation here. So if we cross product e minus d and x minus d, we have a line segment dx and a line segment de. But we're doing a more general cross product that works with any line segment, not just ones that share a vertex like this. Okay, so you might have points outside the hole and inside the hole. In the second part, I will pass in numbers, and you have to tell me if that point in space is in the hole or if it's out of the hole. Okay, so we've got 2 guys here. Okay, so let's see. Double x1 is equal to left-hand side's end minus left-hand side's start. So that's how far to the right the line goes. Double y1 is equal to left-hand side end dot y minus left-hand side dot start dot y. So this is how far up it goes. And so for the first line. So let me draw this visually. So I'm writing a function that's going to cross product 2 line segments. So let's say I've got this line segment and I've got this line segment. Okay. So this one I'm calling left-hand side, this one I'm calling right-hand side. So let's say this is at 10, 10. That's the start point. And this is at 30, -5 or something like that. That's the end point. And then RHS dot start is this point here, 30, -5, and then right hand side dot end is going to be at, let's say, 50, 10. Okay. So what we need to compute is how far to the right and how far up and down the first segment is, and it's going to be 30 minus 10. So it's 20 to the right, and it is 15 down, right, for the first one. And then for the second one, 50 minus 30 is also, let's make it 60 so they're not the same numbers. So it's going to be, it's going to be 30 to the right, and it's going to be 15 upwards. Okay. So it's 15 down and 15 up. Yeah. Fair enough. Okay. Such is life. So, yeah. So this is going to say it's 20 to the right and 15 down. And then for this one, x2 is equal to right-hand side dot n dot x minus right-hand side dot n dot start dot x. Sorry. Double y2 is equal to right-hand side dot n dot y minus right-hand side dot start dot y. And then we simply return x1 times y2 minus x2 times y1, cross product. And there we go. So this function here will, so if we're given these two line segments here, let's do the math on it. So x1 is 20 because it's 20 to the right on the first line segment. y1 is equal to negative 15 because it goes down 15 to the right. x2 is 30 to the right, and y2 is 15 north. And so when we do the computation, it is x1 y2 minus x2 y1, which is 20 times 15 minus 30 times negative 15. So that is 200, 300, 300 minus negative 300, negative 450 minus negative 450. And so the answer is 750. So this is a positive number, so it's a left-hand turn. Okay. Positive number, turn to the left. Okay. So, might even just, I don't know, want to make it a Boolean, right? Return, return the sign or something like that. But yeah, there you go. So you just pass in two lines to it. You just call, example, line Bob is equal to 10 to 30 negative 5, and Sydney is from 30 negative 5 to 60 10. See out cross product Bob Sydney will print 750. If I'm doing the math right, there's no guarantee. We'll print 750, which is positive, which means it is a left-hand turn. Okay. So this is one line segment going from 1010 to 30 negative 5. This is one line segment going from 30 negative 5 to 60 10. And if you cross product the two of them, you get a positive number. That means that that's a left turn. And so what you do is you so push onto the stack 10 10 to 60 10. Okay. Does that make sense? So you've got this line, you got that line. Since that's a left-hand turn, you pop them off and you push on a new line containing that start and that end. And then you check to see if it's a left turn again. That's about it. Okay. So, have any of you guys worked on the whole assignment yet? Okay. There's the new linear.h. So, that's you got till Friday to do that. It should be probably a couple hours of work, but it'll be a good exercise for you. It'll kind of pull together. It'll kind of pull together the different things we've been talking about this semester. So, yeah, computational geometry is fun, and it really underlies a lot of 3D graphics. If you look at these big brain geniuses like John Carmack, and I'm not using that term sarcastically at all. Like, I literally mean John Carmack as one of the greatest minds in computer gaming. And if you look at what he does, he reads papers of computational geometry or computer graphics. There's different names for the field. But like, he'll read about a new data structure and he's like, oh, that's interesting, and he'll implement it. Or he'll like see somebody's idea for like mega texturing. He's like, oh, that looks interesting. And so he'll build a brand new computer gaming engine just to see if mega texturing works, which is where Rage came from, the computer game Rage. And so being able to do this kind of stuff will make you better at making computer games, yeah, but also like, if you ever had to work on a gaming engine, definitely would help with that. But I think just in general, having a good fluency with linear algebra and computational geometry is just one of those things that, like, it seems like it just is really useful as a games programmer. Maybe, maybe not if you're doing game code, but even then, you do a lot of dot products and cross products, and just having general fluency with that kind of stuff. Yeah, it's good to just be good at it. Even if you're not making a complex whole per se, if you're making laser guns and things like that, just, yeah, you're gonna make a laser that, has to do a little bit of vector math to figure out where the end point is, and if it's gonna reflect, then you gotta know how to do a reflection around normal, and yeah, it's good for you. So that's your homework assignment. You got 2 days. Have at it, and we will pick it up again tomorrow. Okay, see you guys. Any insights on modding? Yeah. I'll talk to you offline.